So, welcome everyone. Let me so what I want to do today is introduce Harish-Chandra map for Clifford algebra. So maybe something you're not so used to, but it's quite simple. So I guess it shouldn't be a problem. And then see what it looks like when we do some restrictions on it. So first, let's do the setting. Our Lie group will be SL odd. Why is it odd? I will tell a bit later. So maximal compact subgroup will be SO. So we have a standard Cartan decomposition, and in this case, dimension of K will be n times 2n plus 1, and dimension of P will be n times 2n plus 3. Notice that the parity of the dimension of P is the same as the parity of n, which will be important later because some proofs look slightly different in the case of n even and n odd. For n odd, it's slightly more complicated. So yeah. Then we are taking a fundamental Cartan subalgebra. So T will be a commutative part of K, and A will be commutative part of P. Now we choose this doesn't look the way it should. This part should be in another line, but okay. Anyway, let's choose our positive and positive roots for K and G. But just be careful, things behave slightly different because we're not looking at them with respect to age, but with respect to T. Which means that our space of root vectors doesn't have to be one-dimensional, for example. Now I can say why we are looking at SL odd and not SL even. In the case of SL odd, here is the thing. Once you choose your positive roots for K, your positive roots for the whole G, or in other words, for the P part, are already uniquely determined, which wouldn't be the case in SL even. So that means that in P, we either have repeated roots from K, or maybe 2 times a root from K or something like that. So it is uniquely determined. And now let's denote by n plus and n minus positive and negative root vectors in G. Also, we will need an invariant symmetric bilinear form, which is non-degenerate on G and P. So now we have to choose some basis. Well, I'm just saying this part for the convenience, I actually omitted the parts of proofs when I'm explicitly using these bases. So first, for positive weight vectors in P, we take E1 to EK and choose them to be isotropic. And F1 to Fk will be negative weight vectors, which are dual to E1 to Ek. Of course, everything with respect to B. If it's not with respect to B, I will say it. Then, about this Cartan part, there will be a slight difference between even dimensional and odd dimensional case, as I mentioned. So if P is even dimensional, then A will be even dimensional as well. And if P is odd dimensional, A will be odd dimensional as well. And as you could see, since the parity will be just the parity of N, every second guy will be even and the rest will be odd. So first, if we have that P and A have even dimension, then we can get something like this. And then we can just put these together and form a basis for P plus and P minus. But if our A and P are odd dimensional, then first we have to choose a vector, let's call it H0, which is isotropic. And then check
no,
the
this
direct...
H0 is not isotropic. All the others are, but not H0. It pairs with itself to 1.
Yes, okay, sorry, you're right. Then we check the direct complement of that element in A, and that complement will be even dimensional, and then we do the same thing again. So sometimes you have to take this guy into account separately. Well, what's actually the main difference? If you remember the definition of the spin module, so in even dimensional case, up to isomorphism, you get only one spin module. And in the odd dimensional case, you get two of them, which are not isomorphic. And the difference is exactly acting on this guy here. Okay, so much about the setting. So yeah, as I said, spin module will be defined as a vector space as exterior algebra of P plus. And as K modules, we can see that we have this kind of decomposition into V lambdas, where lambda is the highest weight of S. What we will also need is this mapping alpha that is defined on K with this formula. BI, DI are dual basis for P. So we do a commutator with BI and multiply it with DI. So if X is an element of K, this part ends up in P, and then this product ends up in the Clifford algebra of P. Here, I just want to mention that we're taking the Clifford algebra with respect to this rule. So xy plus yx is minus 2b of xy. And alpha can be extended to the universal enveloping algebra. So that's what we will consider. So this mapping will be super important to us. Now we have a proposition that we're also going to use, which says that all vectors in the exterior algebra of A plus, which you can consider to be a spin module for A, in fact, are lowest weight vectors for S, and that lowest weight will be exactly minus rho n. Let me remind you, rho n is the difference of the rho of G and the rho of K. Okay. And finally, let's introduce this Harish-Chandra map in the case of Clifford algebra. So we can use Poincaré-Birkhoff with theorem for the Clifford algebra in this way. If we have a basis for P, that's what we are interested in, then these monomials of the form, either we include a basis element or not, these form a basis for the Clifford algebra. So now what we can do is we can, in this order, we can take the basis for P to be, let me remind you, these were positive weight vectors, these were negative weight vectors, and these guys here are from A. Again, H0 only in the odd dimensional case. And now using this basis, we can see that Clifford algebra of P can be decomposed as Clifford algebra of A plus, well, these guys are just positive weight vectors in P times Clifford algebra of P and Clifford algebra of P times negative weight vectors. And with respect to this decomposition, we can define a projection. So from Clifford algebra of P to Clifford algebra of A. And that is what we're going to call Harish-Chandra map. Unfortunately, this map is not even an algebra homomorphism, but we can fix that part by looking at the restriction of this mu to K invariants of the Clifford algebra of P. In that case, not only we get a homomorphism, we actually get an isomorphism. So that's like the first important result.
Isomorphism onto all C of A?
Yes, yes. That is the proof I'm going to briefly show, so now you will see. So, as I said, the theorem states that the restriction to K invariants is actually isomorphism between K invariants and Clifford algebra of A. Okay. As I said, first we have to prove that it's a homomorphism. So what we do, again, we use this Poincaré-Birkhoff-Witt basis. And we conclude that every monomial in the linear combinations of those basis elements in K invariants have to be of T weight 0. And that's why we can conclude that such a monomial belongs to this set if and only if it belongs to this set. And we're using that equivalence to show that the kernel of the restriction of this Harish-Chandra map is actually a two-sided ideal. I didn't want to write that down because it's just a bit of playing with sets, nothing super interesting. So in other words, we get a homomorphism. So moving on, what we know is
Could you go back, please?
That Clifford algebra of P is the same as endomorphisms of the spin module. Okay, to be precise, that's what happens in the case of even dimensional P. So we have an equality like this. In other words, K invariants in the Clifford algebra of P are the same as K endomorphisms of the spin module. Now, using Schur's lemma, we can see that the restrictions of the elements of these K invariants to the exterior algebra of A plus, or the spin module for A plus, can be identified with endomorphisms of the spin module of A. Again, using the same equality, but now not for the spin module for P, but the spin module of A, we have that it's the same as Clifford algebra of A. Actually, we get the same conclusion if dimension of P is odd, but in this case, we actually have to take into account that we have two different spin modules. For P, actually they are isomorphic as K modules, but not as C of P modules. And in this case, we can write Clifford algebra of P as the sum of endomorphisms of the first spin module and endomorphisms of the second one. So since they're not isomorphic, there can be no intertwinings. That's why we get a direct sum. And now we can do the similar thing as before. So we get a direct sum of K endomorphisms of the first spin module and endomorphisms of the second one. And now we do the same thing. We can identify restrictions of K invariants. We identify them with endomorphisms of the spin module of A and endomorphisms of the spin module of A. So we get a decomposition like this. And again, using the same thing as here, but for A, not for P, we get that it's actually a Clifford algebra of A, exactly what we need. And finally, we can notice that every monomial in this part acts as 0 on the spin module of A, because n minus intersect P sends all the lowest weight vectors to 0. And therefore, every k variant A has to act as mu of A on the spin module. So we get an isomorphism. Okay. Now we'll have to define a few more things. Some of you might remember this from another seminar I had, but it was 2 years ago, so if you forgot about it, don't feel bad. So let's denote by E the image of alpha. Yeah, maybe I could remind you what alpha was. So here, this is how it's defined on K, and then we extend it to the universal enveloping algebra. And let's denote by E the image of that map. And let's denote by J K invariants in the exterior algebra of P. And now I want to define so-called primitive invariants. So first of all, let's denote by J plus the augmentation ideal of J. That would be if you have a graded space. Well, J is definitely a graded space because exterior algebra of P is. So as a subset, it is graded. And now you, from the grading, you only take the summands of the degree strictly larger than 0. So for strictly positive degrees, and you get augmentation ideal. And let's look at the orthogonal complement of the square of J plus in J plus. I will denote it by Q, and that's what I'll be calling the space of primitive invariants, and its elements primitive invariants. And we actually know what's the dimension of the space. It actually has to be the same as dimension of A. So in a general case, if you're looking at the primitive invariants in G, then the dimension of the space would be the rank of G. Also, one important mapping I'll be using is so-called contraction operator. We start by defining it on lambda 1 of P. And the result will be, yeah, I forgot to write, X is an element of P. So what it does to a Y that is also in P, it just checks the bilinear form on those. Yes, I'm actually not entirely sure if I'm supposed to write this minus. Pavle, maybe you could help me. But the thing is...
I thought it should be -2, but maybe I'm wrong. Maybe there is some choice, in fact. I don't know.
Well, you can write any complex number with the still family of these super observations.
Well, that's true. Actually, what I need mostly is just to put it into some vector spaces. So yeah, the scalar is not that important, but you know that we're not using the same Clifford algebra as Constant or Maslov, so I'm never sure about the signs. But I guess
it's a mess with all this, with all these conventions. So here, certainly for this definition, you could do any scalar, but I think we want this I of x and then this wedging by x. We want those, the anti-commutator to be maybe the identity, I think. Well,
Yeah,
uh-huh.
it will also make sense from point of view.
Then you can rescale one, but then you should rescale the other. So I'm not sure, but it doesn't matter. I mean, it's when you write some proofs, then you have to be very careful. But for just an exposition, it doesn't matter whether it's plus or minus or 2 or minus 2.
Oh, I just remembered. There is one thing I also forgot to write. So yeah, as I said, Maslov and Constant are using different Clifford algebra. Yes, maybe I should mention those parts now. So they put a plus here. And then I remembered that I'm missing a coefficient here, actually, which will be important later. But actually, we put here minus 1/4.
Mhm.
And I'm not sure about Constant, probably him as well, but he's defining so many mappings that it's not hard to get completely lost. But Maslov is actually using the opposite sign. So his results turn a bit differently, but okay, up to a sign, it should be the same. Okay, now where was I? Okay. So we define this contraction operator on P, and then we can extend it to the whole exterior algebra by using this rule. So we actually want to get a derivation. Here, this guy denotes the degree, this in the gradation, the degree of U. And all of this was important, first of all, because Constant proved that the Clifford algebra of P is actually a tensor product of this image and these invariants. And it's called the row decomposition because this E part actually can be written as endomorphisms of V row. And also we have that J, so these K invariants are a Clifford algebra of the primitive invariants, although not the standard Clifford algebra. We have to change the bilinear form a bit, change some signs in order for it to really be isomorphic. And that's actually Clifford algebra variant of the so-called Hopf-Kožul-Samuelson's theorem. That one states that J is exterior algebra of Q. So Constant did this Clifford algebra analog. And now we want to see what our isomorphism, Harish-Chandra isomorphism, does to E part. Well, since we're only looking at K invariants, which will be a subset of T invariants, we first want to see that T invariant part of E, so this image of alpha, are just constants. And we do that in 3 steps. First of all, so yeah, that factor -1/4 is kind of important here. First, we prove that we get minus rho if we look at the image of mu compose alpha on elements of the Cartan subalgebra. Then we prove that if we take an x to be a positive root vector in K, then we actually have that alpha is sending that guy to this part here. But if you remember, as I was making comments about this Harish-Chandra map being a homomorphism, this part is actually inside of the kernel of mu, and that's why mu of alpha of x has to be 0. So these 2 parts, we prove them by taking those bases I mentioned at the beginning. And then you just, well, in the first part, you just use the fact that T is a commutative algebra. Then in the second part, you just look at your summands and show that each of them has to be here. And finally, what we want to see is how mu compose alpha acts on any monomial in universal algebra of K, well, the T invariant part. So what we do is we take A's to be positive weight vectors. We take B's to be dual negative weight vectors. And these G's will be a basis for T. And now we're looking at 2 cases. First case is if these A's appear in the monomial. If they appear, then alpha of that monomial is actually in alpha of this first guy, because there is a first guy, times Clifford algebra of P, which is, by the previous step, inside the kernel of mu. So the whole monomial goes to 0. But if A's don't appear, then B's don't appear as well, because we're looking at T invariants. So we have to have T weight 0. In that case, we get that M is just some product of G's. So actually, it's just the product of elements in T. But our first part of the proof was that mu of alpha is a constant on elements of T. So we just put that into our equation, and since we're talking about homomorphisms of algebras, we can write it as mu of alpha of the first guy, mu of alpha of the second guy, and so on. And this guy is minus rho of GJ1. This guy is minus rho of GJQ. So in the end, we just have some products of rows. Well, anyway, we get a constant. Exactly what we want. And now, this is the only part that I can't prove at the moment, but hopefully I will be able to do so soon. Remember that contraction operator? That was this iota. So Kostat claims that if we apply any contraction to a primitive invariant, we actually end up in the image of alpha. Well, why is it a bit problematic to prove now? Because in his case, he's considering this case when G is actually G plus G. So it's his K and P are mostly interchangeable. And in our case, they're not, because we are actually concentrating on P and letting K act on it. So now we're having some troubles of setting things as it is, but let's assume that it's also true in our case. Then, if we take X not to be in P, but in the commutative part, then we don't just end up in the image of alpha, but we also end up in T invariants. And I just proved that mu is sending these guys to complex numbers. So yeah, as I said. And I'll be using that to prove, well, first I need a small lemma, but we're basically there with the main result of this whole presentation. So first, we notice that for all ages in A, and U being in K invariance of the Clifford algebra of P, we have that, well, mu and so Harish-Chandra map and the contraction operator kind of commute. And that will be important for the final result. Well, I already put some spoilers, since I wrote identifying Q and A. So yeah, that will be the main result, that the Harish-Chandra map actually gives a bijection between primitive invariants and the commutative part of well, okay, I think we're ready to get to the main result. Well, first of all, this result is kind of surprising. Well, why? The image of the Harish-Chandra map is the whole Clifford algebra of phi. And now this theorem claims that primitive invariants end up exclusively in the first degree. Well, okay, I'm not sure if it's politically correct to talk about the first degree in the Clifford algebra, but, well, if it was graded, then this would be like the component number one. But okay, we can talk about filtrations. So yeah, in that case, I guess it's fine. And now I didn't really discuss these primitive invariants a lot, but the thing is, we are inside of J plus. So first of all, we cannot be in degree 0, but we also cannot be in degree 1 or 2. The lowest degree that allows existence of primitive invariants is actually 3. Well, I didn't write it down, but we actually know exactly in which degrees primitive invariants can appear. And we know that if we know the exponents of our Lie algebra. So it is quite weird that our primitive invariants under the Harish-Chandra map behave as elements of degree 1. You actually get a similar thing in Constant's row decomposition. Also the part I didn't write down, but here you actually get that the primitive invariants behave like elements of degree 1, which they're definitely not. So they usually come in much higher degrees. So, oops, it's too early for this one. Okay, let's prove it. Well, we have the most ingredients, we just have to kind of put them together. Well, let's take a primitive invariant and let's take any age in a part. Then, since this part here, as I mentioned, is in T invariants of E, then mu has to send it to complex numbers. And let's denote by Q the image of P under the Harish-Chandra map. So we can actually write that the contraction for any age applied on Q is, by definition of Q, this guy. But using this last lemma, we can write it as mu of iota h on p, which is, as I just said, in the complex numbers, or you can also look at it as the zero grading component of A. And remember that this iota was defined on P with a bilinear form, which is non-degenerate. And now, since it's not degenerate, this element we get has to come from some element H1, because B is non-degenerate on A. So there has to exist some H1 such that this number here is exactly iota H applied on H1. And now we observe that the intersection of all the kernels of the contraction operators, well, of the elements of A, are just constants, which means that H1 and Q have to differ by a constant. In other words, Q can be written as this H1 plus some constant H0. But we know that the Harish-Chandra map is a map of superspaces, and P is an odd element. Yeah, maybe I didn't mention that part. I said that we know in which degrees our primitive invariants can appear, but they're always odd. In other words, the even component of Q has to be 0. Or, well, this H0 has to be 0, which means that Q is exactly H1, and H1 was taken from A, so Q is in A, which means that Harish-Chandra map took the primitive invariant to A. So now we have that Harish-Chandra map applied on all primitive invariants has to end up inside of A. Okay, good. But Q is a subset of K invariants in the Clifford algebra of P. And we already proved that over there, mu is isomorphism. In particular, it's injective. So mu has to be injective on Q as well. And also I mentioned that some point that Q and A have the same dimension. So we have an injective mapping that has the same dimension of the domain and codomain. So it actually has to be isomorphism of vector space. And that's pretty much it. So thank you for your attention.
Okay, that's good. So there is just this one missing little step, right? This constant thing. Yeah, so I started reading, but I haven't yet come anywhere.
Oh, really, so many letters that I don't know, somebody should make a map how to follow it all around.
I agree.
Yeah, actually, I'm really grateful to Baslov that he wrote some of those things in a much more understandable way.
Baslov. Yeah, him I haven't read yet at all. Now I'm trying to decipher Meinrenken's book, but I still don't know what exactly he has. So I was like reading and reading, but
yes, actually, maybe it's worth mentioning. Baslov has a slightly different proof that Harish-Chandra map is actually an isomorphism on K invariants. But I kind of took part of that proof, but for some other things. This proof that I showed is, well, ours. I think me and Pavle can take credit for that one. So yeah, but if you're curious about other version of the proof, I can show it to you.
So do I understand it correctly that these primitive invariants are determined by the degree 1 component?
Degree 1 component where?
Like if I take some primitive invariant, some element of Q, then it's in the odd part, right?
Yes.
And this Harish-Chandra map just sends it to degree 1 part.
Yes.
So it means, and it's isomorphism. So it means that this these higher components, like the degree 3, 5, whatever, are just determined by the first degree somehow.
Well, the thing is, in the primitive invariants, you are not going to have the first degree part.
no, well, I mean, it's not a graded algebra, but when you write the monomials, the PBW monomials, then there is this. So what Harish-Chandra map takes is just the projection, right? So it picks this degree 1 component. I think Vit is right. But you have to write it first in this particular PBW. I mean, PBW is not unique, right? But here we took this specific basis, and then it reads off just this A part. But for the primitives, A part will be linear. So yeah, it's the degree 1, because the other invariants that are not completely in A, all these other monomials, they will have to have something from P plus, or from this N plus intersected with P, and also something from the other side. So they cannot have degree 1 anymore. But here by degree, by the degree we mean degree in this PBW sense.
Yeah, that's right.
So it's not some very nice degree, but for that degree, I think you're right.
No.
I think some low-dimensional examples to see what's going on, concretely in dimension, I don't know, 5 or 3.
Yeah, I should have done that. Well, maybe I could type it down for SL5, let's say, and then send it to you.
Oh, send it to everybody or show us next time or something.
There's some weird sound.
Что se to čuje?
Some interference, I think. I don't know.
Yeah, so I think it's maybe interference because Carmen and Hrvoje have both microphones in the same room, so maybe one
Probably.
is hearing the other. Maybe that's the issue.
But how did we
There is
survive for
some-
the whole hour without that?
There is some
Because Hrvoje was
Tacoma
muted.
bridge about to break apart.
Until now, I was muted, so
Can you just make the computers face each other so we can kind of look into this infinite mirror?